We are looking at force versus time graphs. There's a mass of 2.1 kilogram involved in this problem. Okay, first of all, what is the area bound by the slope and the x-axis, right? That's called the area under the curve. What does that represent? So you can see the area is force times time. Okay, and recall, when you take force and multiply it by time, you get impulse. Right? So what is the impulse for the first 4 seconds? So during the first 4 seconds, you have this area right here. So the area is 1/2 of the base times the height, which is 1/2 times 4. And the height is also 4. And that's 8. The correct unit for impulse is the Newton multiplied by the second, so Newton seconds. Number C, what is the impulse for the time interval 4 to 8 seconds? So from 4 to 8 seconds, you have this box right here. So for that one, it's a little bit easier, right? Area for a rectangle is just length times width. Length is 8 minus 4, which is 4. And then the width or the height is just 4. So you have 16 Newton seconds. Okay, see if you can beat me to the impulse for the 8 to 10 seconds interval. Right, so impulse is equals to area, which is 1/2 base times height, 1/2 of 2 times 4, which is just 4. And I can see some of you guys can do that in your head. Okay, so now we're looking for the total impulse between 0 and 10 seconds. So the total impulse from 0 to 10 seconds. And since we've already calculated them individually, let's just add them up. Okay, that's 8 plus 16 plus 4. That's 28. What is the change in momentum, and how does it compare to the impulse? Recall the impulse change in momentum theorem. Impulse momentum theorem says impulse is equals to change in momentum. And it's that easy. If you recall the theorem, you can simply put the change in momentum is 28. But the correct unit of momentum would be kilogram times meters per second. Right? And it's equal to the impulse. Okay. We're looking for the change in velocity in the next section. change in velocity. Okay, so we can start with change in momentum is equal to mass times change in velocity. So all we have to do is isolate velocity by dividing both sides by the mass, just like that. We already found the impulse, or the change in momentum, would be 28. The mass, you have to go back up to the problem from earlier, and I believe it was 2.1 kilograms. Kilograms cancel. I think I missed a decimal too. Just go ahead and divide it out. What is it? Okay, 13.3 meters per second. Any questions about that section? Alright, we have a 5 kilogram object dropped from rest. Alright, so let me just put V initial is equal to 0. Height of 44.1 meters. It takes 3 seconds to fall, and the velocity right before hitting the ground is this thing. Okay, so that must be your V final. Calculate the net force acting on the object. Net force acting on the object. So what we have in this unit is force times time equals to mass times change in velocity. Since we're looking for the force, we're going to divide both sides by time. Okay, so 5 kilograms. Change in velocity, you're going from rest to 29.4, so your change in velocity would be 29.4. And then the time that it took was 3 seconds. Okay. The units look pretty messy, but if you recall that a force comes out to be a Newton, you should be okay. So 5 times 29.4 divided by 3, that's going to give you 49 newtons. Okay, let's graph this over time. 1, 2, 3 seconds, and that 49 newtons. Right, we can assume that it's constant. So what is the area under this curve, even though it's a straight line? So we're looking for this area right here. So the area is equal to length times width, or 3 times 49. Okay, and that's 147 Newton seconds. And this represents the impulse, right? Impulse. What is the change in momentum? Well, it's the same as the impulse. Right, notice how I'm speeding things up a little bit because we've already done a similar problem. Okay, so now it says calculate the impulse applied to the object, and that's just a impulse is equals to force multiplied by time, and we've actually already done that. This is a repeat, and you can just bring this down here. It's a repeat. Okay, so what's the correlation between area, change in momentum, and the impulse? So you can conclude that area of a force versus time graph is equals to change in momentum, and that's equals to impulse as well. Here we go. Bobby and Betty have identical masses, and they're going cliff diving. Bobby lands on a rock. Of course, it has to be Bobby, right? Betty lands safely in the water. She probably paid attention. Answer options are Betty, Bobby, and same. Okay, which person had the most momentum when they reached the bottom, just before impact? Right, so assuming that they both jump from the same cliff, with the same mass, you would expect the momentum, the final momentum, since they have the same mass, and since they jump from the same height, they're going to reach the same velocity. So you would expect the momentum to be the same. So when they hit the rock or the water, they're hitting it with a momentum of P final, but then eventually that P final becomes, when they both stop moving, their final momentum is 0, right? So correct answers to this one should be the same. They're going to lose the same momentum. Okay, the question is, which impact took the most time? Well, Betty, Bobby, which one took more time? It's Betty. Betty took more time because she landed in water. Water takes more time to stop you than a rock. Which impact had the most force? Bobby. Less time means more force. Which person experienced the most impulse? Okay, remember impulse is the change in momentum. So technically they experienced the same impulse, the same change. Okay. Okay, why is Betty safe and Bob? I don't think he's broken. I think he's dead. Okay, Alex. For these comparisons, what you want to pay attention to, what's most important to, is the system you're looking at. So for example, on the left side, we're looking at two objects. Okay, so, and then on the right side, it's just one object, and that's very important. So let's look at the difference. On the left-hand side, you have a bug colliding with the windshield of a car. I'm going to use these inequality signs and equality to describe each of the following relationships between the bug and the car. So from first semester, we know that when two objects collide, the forces they apply on each other should be equal. And if you recall, that's third law, right? That's Newton's third law. Now that's between two objects. Okay, the relationship between the times of impact. The bug is colliding with the car. They have to be equal, right? Because that's the whole system. Relationship between the applied impulses. This is where it's going to require some thought. Okay, so we already said that the forces are the same, the times are the same, so impulse must be the same. Yes, but impulse is also force multiplied by time. Okay, so Ross said, isn't impulse also the change in momentum? Yes. So the impulse is the same, the change in momentum is the same. What is different? Yeah, if you're a truck, a bug is not going to change your velocity very much. But if you're a bug, you're going to get turned in the direction of the truck. Right, so the change in velocity of the bug is going to be much greater than that of the car. Okay, so now we're looking at one object. A car crashes into a very, very strong barrier. Describe each of the following between a collision with and without an airbag. So our focus here is just the driver. Okay? So our focus here is just the driver. The driver with an airbag versus without an airbag. The driver with an airbag will experience a smaller or larger or equal force. Hopefully smaller, right? The relationship between the times of impact. Airbag gives you more time, right? Airbag gives you more time versus a windshield or a dashboard. Okay. The relationship between the applied impulses. With or without an airbag, the body of the driver has to come to a stop. So the impulses will be, or their change in momentum would be the same. So you can start with that one first and then go back and answer this one. Okay. Whether you have an airbag or not, your change in velocity would be the same because your body comes to a stop. Okay,